Good morning, everyone. Let's start. In the previous class, we had a discussion about various kinds of variable length code. So we're basically looking at basic properties that a good zero error variable length code should satisfy. And some of these are just purely matters of convenience because I want to be able to encode or decode efficiently. All right, so we first saw the most basic property. If you want zero error, then the code must be non-singular. So two symbols cannot have the same code word. But then we then realize that if you want to, we also may be interested in encoding not just symbols but sequences of symbols, and we want to do this as efficiently as possible. So that led us to the idea of uniquely decodable code. So it's not just that two symbols should not have the same code words. Even if you look at arbitrary extensions of the code, then the extension should also be non-singular. Okay. But we saw another special class of uniquely decodable codes called prefix-free codes, wherein we want to make sure that no code word is the prefix of any other code word. Now, every prefix code, as we saw, is uniquely decodable, and every uniquely decodable code is not singular. But the other way around is not true. It's of course obvious that a non-singular code cannot, sorry, a singular code cannot be uniquely decodable. But at the moment, we've not seen codes which are uniquely decodable but not prefix free. We'll see that in a moment. And right now, it may not be obvious why they demand prefix free codes, but in this class, we'll see why prefix free codes are important and what they bring in addition to uniquely decodable codes. All right. Any questions from any of these topics? Okay, so just to make sure that we've got all of this, let's see an example. Okay, so here I have four codes. Okay, there are four symbols. The alphabet is A, B, C, D. All right, the alphabet is A, B, C, and D, and the corresponding code words are in this table. So let's look at code C1. Just a point, I mean, if you've not joined the Google Classroom, please send me an email. Okay, so let's look at the first code. So A gets mapped to 0, B gets mapped to 0, 0, C gets mapped to 1, 0, and D gets mapped to 0, 0. Now how do you classify this particular code? Is it non-singular? Is it uniquely decodable? Is it prefix-free?
A is prefix for B and D.
Okay, it's not prefix-free, but first of all, is it singular?
Not singular.
So can you repeat?
Is the code non-singular?
No, sir.
It is not, right? Because both B and D have the same code word. All right, so this is a singular code. And since it is singular, it cannot be unique. It's of course not uniquely decodable and therefore not prefix free. Okay, now let us look at the second code. Is this non-singular?
Yes, sir.
It is non-singular, right? Because all the code words are distinct. So obviously it is non-singular. Okay, is it uniquely decodable? is this code C2 uniquely decodable? So if I look at extensions, if I take the concatenation of two symbols or number of symbols and look at their the corresponding code words, the code words always be distinct.
No, sir.
No. So can you give me an example of code words which are the same?
So CA and B.
Okay. C, A, and B. So the encoding of CA, this is equal to C is 0, 1 and A is 0. So this is 0, 1, 0. But the encoding of B is also 0, 1, 0. So there's no way of distinguishing the two. So therefore, this is not uniquely decodable. So it is not a uniquely decodable code. If it is not uniquely decodable, then it is of course not prefix free. And that is obvious from this because you see, I mean, so this is a prefix of this. Also, this is a prefix of this code word. Right? So it is not a prefix free code. Okay. Let's not go to this C3. We'll explore C3 in a little bit. Let's go to C4. Is it non-singular? So we're looking at C4. Is it non-singular?
Yes, sir.
Yes, sir.
Yes, it is non-singular. Okay. Is it uniquely decodable? Or let's jump to prefix free. Is it prefix free?
Yes.
It is prefix free, right? So since it is prefix free, it's also uniquely decodable. This is prefix free, and therefore it's also uniquely decodable. Okay, that's good. So now let's go to C3. Is this non-singular?
Yes, sir.
Yes, sir.
It is non-singular. Is it prefix free?
No.
No, sir.
It is not prefix.
It is not perfect.
Good. Not prefix free. Now the question is this uniquely decodable? My claim is that this is a uniquely decodable code.
Sir, this
Yes.
can you just tell like not prefix free means like how like which one is a prefix for?
Oh, okay. So for C3, so this is the prefix of this code word, right?
Fine.
Okay, so it's not a prefix-free code, but the claim is that this is uniquely decodable.
Yes, it's uniquely decodable.
Sorry?
It's uniquely decodable.
Yes, it is uniquely decodable. So let's see which code word might cause a problem. Okay, do people agree that this is a uniquely decodable code? Do you see that this is a uniquely decodable code? Or do you think, no, it may not be uniquely decodable?
I think it's uniquely decodable because 110 when we consider an example.
Okay.
So if I get 110 and then it is again one more zero, then I will take it as 11 and 00. That is C and A.
Correct.
So if 110 is followed by a 1, then I'll take it as D followed by some other symbol.
Okay, that's a point, but then that is just for like one or two symbols, right? So you also have to convince yourself, no matter how many symbols I concatenate together, you will never come up with this issue.
Said here, if we took a concatenation of A and B, we will
Okay.
get 0, 0, 1, 0.
Okay, so your concatenation of A and B. Okay.
Yeah, we will get 0, 0, 1, 0.
Okay.
And if we took A and C, we will get another extension, which is
Okay.
not equal to A and B.
Okay. You take A and C, then you basically get 0, 0, 1, 1.
So we won't get the same extension for both concatenation.
Yes, but then you'll have to think about all possible concatenations, right?
Oh, yes.
Right. So let's think about it. So how would you kind of decode? Let's say that I give you a sequence of code words. How would you possibly decode? So let's think about it. Suppose that you see some sequence of code words. Let's say 1 1, 1 1 0, 1 1 1 0, 0 0, 1 1 0, something. Okay. Now at any point, if you see two zeros, two successive zeros, then it has to be an A. Do you agree?
Yes.
Right. So if you observe two successive zeros at any point, then you're 100% sure that it is definitely going to be A. Let's maybe write this down separately.
Sir,
Yes.
two successive zeros can also be a concatenation of B and A, right?
B and A. Okay, fine. So then it would be a concatenation of three successive zeros, right?
Sure. Okay, fine, sir.
All right. Okay, that's a good point. So if you see a run or a sequence of even number of zeros, right, followed by a 1, then it is going to be a sequence of A's. Okay. But then if you see an odd number of zeros followed by a 1, it could be either B followed by A or D followed by A. But anyway, let's focus on the case where you have an even number of zeros between two ones. So let me just write this down on one side. Okay, so even number of zeros implies that these are all going to be A's. Right? So when I say even number of zeros, it means that the zero is either there's nothing before the zero, or before and after the zero there is a 1. Okay, so it's either 0 0 0 0 0 0, and after this either this is the end of the sequence or there is a 1, and before this it's either the start of the sequence or there is a 1. There can't be a 0 in this case. Okay, so that is easy. If you see an even number of zeros, you start decoding, At some point from this point onwards, if you see an even number of zeros, then you know it's a sequence of A's. If it is an odd number of zeros at some point, you're not sure that there could be some ambiguity. Okay. Now, if there is an if there is an odd number of ones, all right, so if there is an odd number of ones, then what can you say?
It's an odd number of zeros?
No, odd number of ones. So it's a sequence of odd number of ones.
C followed by B.
Correct. So it is definitely going to be C followed by B. So it means it's a sequence of C's followed by B, and this will always be followed by a zero. Right? You cannot have an odd number of ones and then ending. Right? So this will be followed by a zero, and this will always be a sequence of C's followed by B's, followed by a B. Okay, nothing else can happen. No other combination can possibly happen, right? Because for D it has to end with a single zero, right? So now there are two more cases. Either you can have an odd number of zeros or an even number of ones. In either of these two cases, where we haven't really determined what is going to happen, right? So the real complicated case is when you have an even number of ones. Right? So if you have an even number of ones, then what can happen? Say even number of ones followed by so it's just even number of ones, and then it ends, or an even number of ones then followed by some zeros. So suppose you have an even number of ones and then it ends with that. Then what can happen? Then what should happen?
String of C's.
It's string of C's. Right? Nothing else. It can't be any other combination. Now, what about even number of ones followed by some zeros?
C's and C's followed by D's.
C's and
C's followed by D's.
correct, but it could also be an A, right?
Yeah.
So you have even number of ones followed by a certain number of zeros, right? If it is an even number of ones followed by an odd number of zeros, then what must happen?
C, D, and
CDA.
several A's.
It will be a sequence of C's, and then there's an odd number of zeros. So it could either be C followed by a D and then A. Anything else happen?
Odd number of days?
No.
An odd number that happened, right? Because I'm saying that it's even number of ones followed by only zeros. Right? If you had multiple D's, then it would be 1 1 0 1 1 0 and so on. Right? It would just be all C's followed by D and nothing else. It could be a sequence of C's followed by D followed by a certain number of A's. Can anything else happen?
No, sir.
Nothing else can happen, right? Okay. And if the number of zeros is even,
Several
number
C's followed by
of-
multiple A's.
yeah, so then it must be the case that it is several C's followed by several A's. Okay. Okay. So now we've taken care of even number of zeros, odd number of ones, even number of ones. Now, can a code word start with odd number of zeros, or can any sequence start with an odd number of zeros?
No, sir.
No, right? Of zeros, this never happens. So here is a decoding rule. You start from the very beginning. Okay, you start from the very beginning and then count the number of zeros and ones. You start. You see the code word, all right? Maybe the code word is some. Maybe if the code, let us see. So suppose that the code word or of the extension starts with zeros. Okay, you count the number of zeros till you hit a 1. Okay, if the number of zeros is odd, that can never happen. You can never have an odd number of zeros. So the number of zeros must be even. All right. So if it's an even number of zeros, then you know that it's just a sequence of A's. All right. So which means that this must be a sequence of A's. And so from up to this point, you have already decoded. So you just remove that part and then start decoding from this point onwards. Okay, so that is fine. Now, the only issue happens if you see if it starts with a 1. Right, so suppose that it starts with 1, you count the number of ones until you hit a 0. If it is an odd number of ones, then you know it is going to follow with at least 1 0, right? So if there is exactly 1 0, then it is just a sequence of C's followed by a B, right? So if it's odd number of ones, then you know that this followed by 0 corresponds to a sequence of C's followed by a B. On the other hand, if the number of, if this is odd. On the other hand, if you see a sequence of ones, which is even, if you see an odd number of ones, then it can either be just a sequence of C's, or it could be a sequence of C's followed by a D followed by a sequence of A's, or it could be a sequence of C's followed by a sequence of A's. Right? And you need to be a little careful with either case, but in any case, it's going to be some sequence of C's followed by something else. So basically, you just count the number of ones, and then after that, if there are an even number of ones, then you count the number of zeros after that. If the number of zeros is odd, then it is a sequence of C's followed by D followed by a sequence of A's. If the number of zeros is even, then it's just a sequence of C's followed by a sequence of A's. Right? And once you've decoded up to that point, fine, you know what the raw symbols are up to this particular point, and then you discard everything that you have already decoded and then start decoding afresh from this point onwards. Okay, so no matter what sequence of code words you observe, doesn't matter what the extension is, you will always be able to decode uniquely, right? So there is never any confusion, even if you look at arbitrary extensions. Okay, so this is a decoding rule which allows you to uniquely decode any sequence of code words. But for this, we really have to count the number of ones and the number of zeros. That is one way of doing it. Right? Any questions here?
So can we generalize? Here there are only 4 code words, so we can do this. When the amount of code words increase, I think it will be very difficult for verifying in this way.
Exactly. So if the number of code words is big, then decoding can be quite a problem. So there's another problem with this particular code, and the problem is that now let us say that I observe. Okay, so let's look at, so where is the confusion? The confusion is over here, right? So it is, suppose that you see an even number of zeros, even number of ones. C for so let's take something else. Yeah. So suppose I have an even number of ones. Okay. No. Let me take a different example. Suppose I have 1 1 followed by a number of zeros. My code word is 1 1 followed by all zeros. Okay. So this is my code word. What can this be? Let me copy this here. Right, so this is my code word. What are the possibilities?
Number of zeros is odd, it's a D followed by A's. Otherwise, all CA.
Correct. So it's either C followed by a A's, or it is D followed by a sequence of A's. And this depends on the number of zeros. Okay. So think of an application where let's say you're reading these bits one after the other, right? You read the first bit and then the second bit and then the third bit and so on. Now, when will you be able to say whether the first symbol is a C or a D?
Till we encounter a 1 after all these zeros.
Correct. So basically, you have to read all the zeros. Right? So if you think about the delay involved in decoding the first symbol, it can be arbitrarily large. Until you hit the next one after the sequence of zeros, you can never surely say whether the first symbol is a C or the symbol is a D. Right? So in this example, the delay in decoding the first symbol depends on the number of zeros, right? And it will be arbitrarily large. Right? So you're never really sure what the first symbol is until maybe you've read the entire code word sequence. And if the file is very large, then you can never start decoding the first symbol until you have hit the last particular bit of the compressed sequence. So that is bad. So the delay could be arbitrarily large in this particular case. And the second case is as someone mentioned, the decoding is pretty complicated. All right, so you count the number of zeros, you count the number of ones. It was kind of an ad hoc approach, And if we have a more complicated uniquely decodable code, it is not obvious how one would decode the code efficiently. So decoding may be complicated. Right? So for arbitrary decodable codes, although they have this nice property that you never get two code words of extensions confused with each other, it still seems to be, it doesn't to have enough structure so that you can encode. Encoding is pretty easy. Maybe it's a lookup table and then you encode each symbol one after the other. But decoding can get very complicated. There could be arbitrarily large arrays, and it's not clear how we can efficiently decode an arbitrary uniquely decodable code, right? And that is precisely why we focus on prefix-free codes. As we'll see, prefix-free codes have a very natural decoding algorithm, and for those codes, in fact, the delay turns out to be 0. So we'll just see this in a moment. But any questions regarding these 2 points?
Sir, so here the memory required also is kind of more, because till we encounter a 1 in this case, like we will have to keep a count of these
Correct.
bits.
Correct. So that is right. So basically you could, so there are 2 types of memory involved over here. One is the memory in which all of this is stored, right? The entire code word is stored, and that is typically called so that would be maybe your hard disk or sometimes called the main memory. Whereas when you're decoding, you need a certain memory to perform computations, and that is in the RAM, or the random access memory. So what you're referring to is that you will also need a large RAM, because you need to keep a count, or you need to remember how many zeros you encountered or how many ones you encountered, even to decode a particular symbol. So that's a good point.
Sir, so in general it's not efficient, and for real time application it will definitely hinder.
Exactly. So that is why we'll focus on prefix-free codes, and it turns out that even if we why prefix-free codes are nicer, and that they can be decoded very efficiently, and it turns out that there's absolutely no loss in going from uniquely decodable codes to prefix-free codes. If you look at the optimal uniquely decodable code and the optimal prefix code, it turns out that both of them have the same expected length. Okay, but we'll see more of that later. So let's see why prefix-free codes are nice. Okay, and to see that, we'll see a different representation of any variable length code. So right now, how did we think about variable length codes? We thought of them as a table, right? You have a lookup table where for each symbol you write down the, okay, but these are all binary strings, and you can represent these strings in the form of a binary tree. Okay, so let's take a look at this particular example. So this example we had, it is uniquely decodable, but it is not prefix-free. Okay, so the maximum length of this code, let us call this Lmax. Okay, Lmax is the maximum length of the code word in your code book. So the set of all code words is what I call the code book. So the code book is the set of all code words. So mathematically speaking, this is the set of all ENC of X for X in the alphabet. I'm not looking at extensions. I'm just looking at the symbols themselves and the words corresponding to each. So in this case, the code book is, so I'll refer to the code book using this symbol C. Right. So in this case, code book is 0, 0, 1, 0, 1, 1, and 1, 1, 0. And the corresponding lengths are 2, 2, 2, 3. These are the word lengths. And let's look at the maximum length, Lmax. Okay, what I'll do is I'll draw a binary tree of up to depth Lmax. Okay, in this case it is 3. Okay, so this is a binary tree up to depth 3. And I label the edges of the so given any binary tree this form or any tree for that matter, the topmost vertex, so each of these dots is called a vertex, and each of these lines is called an edge. All right, and the topmost vertex, so as we see, the single vertex at the top, and this particular vertex is called the root of the tree, and the bottommost vertices are called the leaves of the tree. Okay, so given any binary tree, you have so each vertex has 2 edges, right? So the root has exactly 2 edges. Anything in between or any other vertex which is not a leaf and not a root has 3 edges, 1 coming from top and 2 going down, and every leaf has exactly 1 edge incident on it, and that is coming from the top. Right, so if you have any 2 vertices, we say that, so let me call this V1, let me call this V2, let me call this V3. So in graph theoretic terminology, we say that V1 is a parent of V2 and V3, and or V2 and V3 are children of V1. Okay, so V2 and V3 are children of V1, and if you have, let's say, V4, V5, and so on, you typically say that, again, think of this as sort of a family tree. If you had to write your family tree, then you have 2 children, and for that you have a parent. So this is not exactly so this would be a parent of these 2 children, and then this would be the parent of this. So this V1 is typically called is an ancestor of V4 and V5, and therefore V2 and V3 as well, or V4 and V5 are descendants of V1. Okay, so this is just terminology, nothing else. If you've not heard of this before, then given any tree, the topmost vertex is called the root, the bottommost vertices are the leaves, and if you have 2 vertices which are adjacent, then the one on top is the parent, and the one below it is called a child. Okay, this is just so that we have some common language to work with. Okay, so now let's look at this specific example. Okay, let me remove all of this. Okay, good. So I have a particular code or code book, and I want to represent this code using this binary tree. So what am I going to do? I will label all of these edges with zeros and ones. So I'll say that for any vertex, the left edge is going to be labeled with a 0 and the right edge is going to be labeled with a 1. Okay, so 0 1 0 1 0 1. So it is some rule. You can, as long as it is fixed, it's a fixed rule, it's fine. So you can label these arbitrarily, except that one of them must be one of the downgoing edges is labeled with a 0 and the other downgoing edges is labeled with a 1. So I'll always stick to the rule that the left edge is a 0 and the right edge is going to be a 1. Okay, so now let's look at this, start from the top. Now, what does this binary tree correspond to? So if you read the labels of the edges as you go from the root to all the possible leaves, it basically enumerates all strings of length L max. So remember that the depth is L max. So the tree basically enumerates or lists all possible, all binary strings of length L max. Right? And if I stop somewhere in between, then it also lists strings of length less than or equal to L max. Basically, I can have all possible strings of length less than or equal to L max. Okay, so now I can map each of these code words to a vertex on this particular tree. Okay, how would I do that? Now let us look at 0 0. Okay, so where can I find? So if I start from the root, where do I get 0 0? I have to read the first edge on the left and the second edge on the left below, right? So this vertex corresponds to the symbol A, right? So by this vertex, I mean that this corresponds to the string 0 0. So there's exactly one path coming from the root to this particular vertex, right? So for any string, any substring of length L max, I can represent it in the form of a vertex because there is a unique path from the root to that particular vertex. All right, so let us look at 0. So B is 1 0. All right, so that is this particular vertex. So this is B. Now C is 1 1. So it is 1 1. So this vertex corresponds to C. And D is 1 1 0. So it is 1 1 0. And it is this particular vertex over here. Okay. So this is a way of representing a code. All right. So I draw a tree. Let me just draw the tree restricted to these particular symbols. So this is a subtree. And I label these 0 1 0 0 1 0. All right, so this vertex corresponds to A, this vertex corresponds to B, this vertex corresponds to C, and this vertex corresponds to D. Right, so no matter which code you give me, right? So each code word is basically, so each code book is basically a collection of binary strings. I can always represent all of these code words as vertices on a particular tree. All right. So the code book is a set of vertices on a binary tree of Lmax. Right, and this is what I refer to. Let me just call this the code tree. Okay, so no matter what code you give, as long as it is binary, I can represent these as vertices on the binary tree. Okay, is this clear? Let's take another example. Okay, so let us say that we have say 0 0 0 1 0, let's say 1 1 0 1 1 1 and 1 0. Okay, this is a set of 5 code words corresponding to A, B, C, D, and E. Okay. Yeah. Any questions? Okay. So now, what is the maximum length? It is still 3. So I'll draw a binary tree up to depth 3. As before, I label the edges with 0 and 1, 0, 1, 0, 1. I'll just to keep things consistent, the left edge is going to be a 0, the right edge is always going to be a 1. Okay, and now I start with the root. So 0, 0 corresponds to this particular vertex over here. So this is A. 0, 1 corresponds to 0, 1, this particular vertex over here, which is B. Now C corresponds to 1, 1, 0. So it is vertex. So this is C. And D is 1, 1, 1. So 1, 1, 1, which is this vertex over here. This is D. And E is 1, 0. So it is 1, 0. This is E. Okay. So this is an example of representing the code words on a tree. Okay. Now let's look at this code in a little more detail. What kind of a code is this? Non-singular, uniquely decodable, prefix-free.
Non-singular.
Okay, is it prefix-free?
Yes.
It is a prefix-free code, right? Because no code word is a prefix of any other code word. So this is prefix-free. Whereas the previous example that we had over here, this was uniquely decodable, but it was not prefix-free. Now, if you think about it, so basically what have I done? I've represented the code words as vertices on this binary tree, correct? Now, if the code is prefix free, then what can you say about the code words or vertices corresponding to each of the code words? Do they satisfy some? Should they satisfy some particular property?
No parents.
Exactly. So no code word, of course, not just a parent. It cannot be any ancestor of any other code word, right? So parent is the one exactly above it, but an ancestor is one which could be anywhere above. So for example, if this is a code word, then this cannot be a code word and this cannot be a code word. So both of these are ancestors of C. Both of these are ancestors of D. If this were a code word, then this and this would be ancestors of this particular code word, and none of the ancestors are allowed to be code words. So that brings us to the observation that so if you represent vertices on the code word tree, then every prefix of the code word corresponds to the ancestors. A prefix corresponds to ancestor on the code tree, right? Or the complete binary tree of depth Lmax. So this means that if the code is prefix free, code implies that no code word is an ancestor of any other code word. Okay, so no code word can be an ancestor of any other code word if this is a prefix free code. Okay, so that's a very useful observation. It's a nice structural property, and this also gives us a very nice decoding rule for prefix free codes. So how would you decode a prefix free code? Let us again take this example. So suppose you had to decode a particular sequence of code words. So what would you do? You start reading the bits one after the other. Okay. If the bit is a 0, then you go left on this binary tree. If it is a 1, then you go to the right of this binary tree. And then you read the next bit. If it is a 0, then you go left on the binary tree. If it is a 1, then you go right on the binary tree. If you have hit a particular code word, if you hit a particular symbol, in this case E, then you know that the first symbol is an E, and then you again jump back to the root, right? So decoding works as follows. You first have the code tree, and then you keep starting from the root. Start at the root and keep doing the following. If the next bit is 0, then go left. If it is 1, then go right. And you keep doing this until if you hit a particular symbol, hit a code word, or basically a labeled vertex. So in this case, the labeled vertices are this one, this one, this one, and these two. Right? So these are the special vertices which correspond to code words. So if you hit a code word, then you output the symbol, and then you go to the root, go to step 1. Right? You start again from the root. Okay. So let's see an example. So again, we'll keep this example in mind. So let us say I have the sequence, say 0, 0, 1, 1, 1, 1, 0, 1, 1, 0. Okay, I'll start from the left. So I'll start with the root. Okay, the first bit is a 0, so I go to the left. The second bit is also a 0. I go again to the left. Now I hit A, so I know that this is A. So then I've reached this particular point. I know at this point that the first symbol is an A. And I again restart from root. Right? I read the first bit from here. It is a 1, so I go to the right. The next bit is also 1. So once again, I go to the right. The next bit is again a 1. So I go to the right. At this point, I have hit D. So I know that the next symbol is a D. And then I again jump back to the root. Now I see that the first bit is a 1. It is this one. It's a 1. So I go to the right. The next bit is a 0. So I go to the left. Now again, I have hit a special symbol. This is E. So I can immediately decode E. And then I again jump back to the root. Now again, the first symbol is a 1. So I go to the right. The next symbol is also a 1. I go to the right. The next symbol is a 0. So I go to the left. So it is C. Okay. So no matter what kind of a prefix-free code you have, you can always write it in the form of a tree, and then decoding is easy. It's just basically a search on this tree. Right? You keep reading bits one after the other, and you can decode instantaneously. So that is why these are called instantaneous codes, because as you see, there is absolutely no delay. When you hit the end of the code word for a particular symbol, you can immediately decode it. You don't have to look at bits in the future. Unlike that example of the uniquely decodable code, where you had to read, where the delay could be arbitrarily large, in this case, the delay is exactly equal to 0. So the delay equal to 0, that's why it is called an instant. Codes are also called instantaneous codes. All right. So we'll stop here. If there are any questions, then I can take them.
So what does the delay 0 mean, sir? Over here, sir?
Oh, by delay 0, that if suppose that you want to decode the current symbol. Okay. So take this example. Okay. So the code word corresponding to the first symbol was actually 0, 0, right? So the code word corresponding to, so this is the actual raw sequence, A, D, E, C, and this is the corresponding code word sequence. All right. If you want to decode only the first symbol, then I only need to read the first 2 bits, that is the code word corresponding to A, right? I don't really need to read anything in the future to decode the first symbol. Do you agree with that?
Yes, sir.
All right. But then if you looked at this previous example, so this code was not prefix free, right? This code word was not prefix free. The code word, the code word corresponding to the first, suppose this was C A A A A A A, then the code word corresponding to C would be just 1 1. Right? So if I want to decode the first symbol, it is not enough if I just read the first 2 bits or first 3 bits. Right? I have to count how many zeros are there following that. Because otherwise I don't know for sure if this is C followed by ace or D followed by ace. So in this case, the delay is the extra number of bits that I need to read in order to recover the first, right? The maximum number of bits in the future that I have to read in the future in order to recover even the first symbol. So in this case, the delay it can be arbitrarily large, but then for prefix-free codes, you don't need to start decoding the next symbol at all. When you reach a particular point, you either know that you have to read more bits for the current symbol itself, or you know that you have finished decoding. You know that immediately, so you don't need to look into the future. So that is what I meant when I said that the delay is equal to 0.
Yes, I got it. Thank you.
All right. Any other questions? Okay, so if not, then we meet next week. So see you all then.